Welcome to this explainer. Today we're tackling KSSCM Form 3 Mathematics, Mastering Scale Drawings. Now this might seem a little intimidating at first glance, but I promise you it's actually incredibly logical. Honestly, it's pretty satisfying once it clicks. If you've ever looked at a map on your phone or a blueprint for a house and wondered exactly how it translates mathematically to the real world, well, you're in exactly the right place. Let's conquer this chapter. Okay, let's dive right into this. Here's our roadmap for what we're mastering today. 1. What are scale drawings? 2. Cracking the 1-to-n ratio. 3. The 3 conditions of n. 4. Calculating actual and drawing distances. 5. Rules for drawing accurately. And 6. Summary and exam tips. All right, Section 1. What are scale drawings? The basics of proportionality. So by definition, a scale drawing is the drawing of an object with all measurements in the drawing proportional to the measurements of the object. Proportional. I really want you to focus on that word. It's the absolutely crucial key to everything we're exploring today. It basically means we aren't just, squishing or stretching a shape at random. Every single side of the shape shrinks or grows by the exact same mathematical rule. Moving right along to Section 2, cracking the 1-to-n ratio, the core formula. Here it is in all its glory, 1-to-n. This incredibly simple ratio is literally the master key to every single problem in this chapter. And the scale of a drawing can also be written as a fraction, where the scale equals the measurement of the scale drawing divided by the measurement of the actual object. That just leaves us with 1/n. Keep in mind, n can be a positive integer, like 2 or 5, or it can totally be a fraction. It breaks down perfectly how that formula is actually split up and applied in the real world. The left side, that 1, always represents exactly 1 unit on the scale drawing itself. The right side, the n, represents how many units that equals on the actual real-world object. 1 is the drawing, n is the object. Drawing to object. Honestly, if you lock that specific order into your memory right now, the rest of this explainer is going to be an absolute breeze. Section 3. The 3 conditions of n. Bigger, same, or smaller? Okay, so there are 3 possible conditions for our friend n, which practically act as a cheat sheet for exams. First up, if n is less than 1, like a fraction, say 1/2, the drawing is actually bigger than the object. I know, right? A fraction making it bigger? It feels totally counterintuitive, but it's absolutely true. Second, if n equals 1, so the scale is 1-to-1, the drawing is exactly the same size as the object. Easy enough. And third, if n is greater than 1, like the number 2, the drawing is smaller than the object. Keep this rule of 3 in the back of your mind, especially that tricky first one. On to Section 4, calculating actual and drawing distances. Step-by-step problem solving. Let's start with a nice and simple one, finding the scale itself. Imagine a drawing where a side is 2 units long, but on the actual object, that exact same side is 4 units long. We just take our formula, drawing over object, which gives us 2/4. Simplify that fraction down, and we get 1/2. This means our scale is written as 1-to-2. Simple as that. You just found n. Now, let's tackle a classic map problem. Say a map has a scale of 1 to 300,000. You measure a river on this map, and it comes out to 3 centimeters long. So, how long is the actual river? Well, step 1, write the ratio. 1 centimeter on the map is to 300,000 centimeters in real life. Step 2, convert those huge object units so they're way easier to handle. 300,000 centimeters is exactly 3 kilometers. So our working scale is 1 centimeter equals 3 kilometers. Now the crucial point is right here at step 3. A river is 3 centimeters on the map, not 1. How do we get from 1 to 3? We just multiply by 3. And the golden rule of ratios is whatever you do to the left side, you must do to the right. Multiply 3 kilometers by 3, and boom, you get 9 kilometers. That's your actual real-world length. Let's try one where n is a fraction, so a square is drawn to a scale of 1 to 1/3. The actual length of the square's side is 6 centimeters. What's the length on the drawing? Step 1, write the scale, 1 to 1/3. Step 2, we know the actual side, the right side of our ratio, needs to become 6 centimeters. Step 3, how do we turn 1/3 into 6? We have to multiply it by 18, because 18 divided by 3 is 6. Step 4, we balance the ratio. If we multiplied the right side by 18, we literally have to multiply the left side, the 1, by 18. 1 times 18 is 18, so the side of the scale drawing is 18 centimeters. Remember our rule from earlier. N was less than 1, and sure enough, Our drawing, at 18 centimeters, is way bigger than the 6 centimeter object. All right, Section 5, Rules for Drawing Accurately. Executing your scale. When it comes to exam time, there are exactly 3 allowed methods for executing scale drawings. First off, you can use grid paper of the same size. So if your scale is 1 to 1/2, you know the drawing is twice as big, and you literally draw every side spanning twice as many grid squares. Second, you can use grid paper of different sizes. Like the question might ask you to transfer a shape from a 1 centimeter grid straight onto a 0.5 centimeter grid. And third, you might just have to draw the whole shebang completely from scratch on blank paper using just your ruler and protractor based on the calculated scale. Now, there's a really fascinating rule here that catches a lot of students off guard. When you scale an object with given angles, the lengths of the sides are drawn to scale, right? They shrink or grow. But the angles of the shape must remain exactly identical. If the original triangle has a 45-degree angle, your massive poster-sized scale drawing of it is still going to have a 45-degree angle. Angles absolutely never scale. You also really need to know how to work backwards. What if they give you the drawing and ask you to find the object? You just reverse the logic. If the drawing scale used is 1 to 2, we know from our conditions that the drawing is 2 times smaller than the object. Therefore, the actual object must be 2 times longer than the drawing. It's really just a matter of flipping your perspective. And finally, Section 6, Summary and Exam Tips, Mastering Chapter 4. Okay, let's wrap this up with a rapid-fire summary. First, the ratio format 1 to n always starts with 1, and that 1 always represents the drawing. Second, watch out for that counterintuitive rule. When n is a fraction less than 1, your drawing is going to get bigger. Third, length, stretch, and shrink, but angles never, ever change. Fourth, always double-check your unit conversions. You know, like taking 300,000 centimeters and making it a nice clean 3 kilometers before you multiply. And lastly, keep your ratio balanced. Whatever you multiply on the right side, you absolutely must multiply on the left. I want to leave you with a quick thought experiment to test your new skills in the real world. Think about your entire school building. If you wanted to draw an accurate scale drawing of it that fit perfectly onto a single piece of standard A4 paper, would your n be a fraction or a very, very large integer? Think about exactly how many centimeters of the real world would need to be packed into just 1 centimeter on your paper. That right there is the sheer power of scale drawings. Thanks so much for joining me for this explainer, and good luck mastering Chapter 4.